present our paper OSAN, a one-stage alignment network to unify multimodal alignment and unsupervised domain adaptation. Here is the motivation. So, extending from unimodal to multimodal is a critical challenge for unsupervised domain adaptation. Two major problems emerge in unsupervised multimodal domain adaptation: domain adaptation and modality alignment. An intuitive way to handle these two problems is to fulfill this task in two separate stages, aligning modality followed by domain adaptation. However, domains and modality are not associated in most exciting two-stage studies, and the relationship between them is not diverged, which can provide information to each other. So in this paper, we unify these two stages into one to align domains and modalities at the same time. In a model, a tensor-based alignment is present to explore the relationship between domains and modalities. By this means, domains and modalities can interact each other and get them to unify information for better reward. So here is our motivation. So we give our motivation on the paper. First, there are two key issues in the multimodal domain adaptation. The first one is how to align the source and the target domains and the remit domain, the descriptor. And the second one is how to align multiple modalities and leverage multimodal information. Most existing traditional methods address these two problems in two separate stages: multimodal alignment followed by domain adaptation. So in this figure, it shows the learning curve of the traditional two-stage models during training phase by 800 iterations for the task and the multimodal semantic analysis. The learning curve is not stable and cannot converge well. So we can obviously see this phenomenon. Therefore, we can observe that there is one obvious weakness in the traditional method. There is inability to preserve the relations between modalities while performing domain adaptation. So in this paper, we designed a one-stage alignment network to unify multimodal alignment and domain adaptation in one stage. The figures shows the scripts of our algorithm. The first, the encoders as multimodal feature extractor map source and target multimodal data to different latent spaces. Then, by means of the effective and efficient way of tensor representation, we propose a TAL modeler to acquire relation information through the interactions between modalities and domains. Thus, the modality and domain are aligned at the same time in one stage. After that, we develop a DDG modeler to mix information from different domains to create new translation domains. Finally, our network is split into three branches, and the first one is the category classification, and the second one is the domain discriminator, and finally is the discrete elimination. In the following two slides, we will give some details of the two important modelers. The first one is the tensor-based alignment, and the second one is DDG. We developed a TAL modeler to address the challenges of multimodal alignment and domain adaptation. We first resort to tensor representation and effective and natural representation of multimodal data to develop models capturing intermodalities and dynamics. Then we utilize statistic measurements to establish an interaction between domains and modality to explore the relation information. In this way, we associate domains and modality so that they can communicate and align together. Especially, we perform tensor factorization to fuse multimodal information and maximize statistics measurement to element and domain gaps at the same time. And in domain adaptation, the adversarial learning is also used to align domains by developing a domain discriminator to judge samples from the source or target domains. By this means, it brings a two-class classification task with hard assignment of 1 and 0. They try to confuse the domain discriminator to learn a shared common representation space between the source and target domains. However, it usually achieves worse performance due to a huge variance between the two domains. To overcome this problem, we propose a dynamic domain generator called DDG to establish a bridge between the two domains. And here we conduct an experiment on two totally different tasks to demonstrate the efficiency of a model. And one task is a popular multimodal sentiment analysis. The other one is a new task called video test classification. In multimodal sentiment analysis, we use two classical data types called CMU-MOSI and CMU-MOSI for this task. To inspect the relative performance of the model, we compare our model with various baselines in three aspects. The first one is a direct transfer, and the UDA method like DAN, ADDA, and MDMN. And the last one is a supervised method like the strong baseline TFN and most recently method MIIM. The overall results are shown in this table. In detail, we find that our method achieves the best result among all the UDA methods and on all metrics with large margin. Surprisingly, our method even achieves better results than many supervised methods such as TFN, MIICE. We conduct another experiment on one other task of video test classification, which is a real industry task for video understanding. The results are shown in this table. All the metrics of OSAN achieve the best result when compared to other UDA methods and direct transfer, leading to a splendid performance of video test classification task. So, in summary, our papers have the following contributions. The first one is to capture the relationship between domain and modality. We propose a one-state alignment network called OSAN to associate domain and modality. In this way, a joint domain invariant and a cross-model representation space is learned in one stage. And the second contribution is we align a TAL model to bring sufficient interactions between domains and modalities and get them to utilize complementary information for each other. And third one is to effectively bridge distinct domains. A DDG model is developed to dynamically conduct multiple new domains by combining knowledge of the source and target domains and exploring extractive structure or data distribution. And finally, extensive experiment on two totally different tasks demonstrate the effectiveness of our method compared to the supervised and strongly UDA method. Okay, thanks, and that's all. Thank you.